I have given you about the influence line diagram for reaction, shear force, and how to draw ILD for bending moment also we have seen, and one problem also I have explained. When two loads are moving on the beam, then greater load at greater ordinate, lesser load on the either left side span or right side span of the center of the section C. Depending on which span is longer, we have to see, and in that side you have to keep, because there in that side you have the very mild slope, other side will be steep slope. Then in the exam you have to see which dimension, which side we have to keep, judiciously we have to judge, and we have to keep the loading on either left side of C or right side of C. That is what I have given. Now let us see if UDL etc. are moving, how we have to manage. Now unlike the units for the reaction, units for the shear force, we do not have any units for that. ILD coefficients for reaction and for shear force, we do not have any units, they are simply dimensionless. But ILD coefficient for bending moment, they have units of meters. Okay. So, first point is that units for ILD coefficient for bending moment are meters. So, only this has units of meter. Second point is, when UDL shorter than the span is moving, how we have to adjust the loads. Okay. Second point, if UDL shorter than the span is moving on the beam, to get maximum bending moment at any section C, keep the UDL such that average load on AC is equal to average load on CV. Now, what is the meaning of this one is, assume that we have a simply supported beam. As usual, here and here there is a ground. This point let us say A, B and C. This distance let us say A. This distance let us say B. Okay, now UDL shorter than the span is moving. You have to adjust the load like this. This is small w, kilonewtons per meter. This length, let us say x, and this length is L1 minus x. That means this total length of UDL is only L1, and that L1 is shorter than the span. Now, ILD for bending moment, we have drawn already bending moment at a section C. It will go something like this. Okay, this is A, B by L. This is your ILD for bending moment at C. This is what you have learned. Then you must adjust the load UDL such that intensity of UDL into area of ILD, area of the influence line diagram must be maximum. Then bending moment at C will be maximum. So, to get the maximum area of influence line diagram, you must adjust the load such that average load on AC is equal to average load on C. Then how that average load is defined is like this. This is the area of the trapezium. To get maximum area of the trapezium, you must adjust the load like this: x by A is equal to L1 minus x by B. If that condition is satisfied, you will get trapezium area maximum. That means loaded length by span must be equal to loaded length by span. In other words, whatever ratio C cuts the beam AB in the ratio of A by B, in the same ratio the C must cut the load also. That means x by A must be equal to L1 minus x by B. Same ratio must be there. Like that. Then you will get maximum bending moment at the section C. It is not absolute maximum bending moment. At a specified section C, I wanted maximum bending moment. At some other section, I may get more maximum bending moment. I am not interested. At C only, I wanted maximum bending moment. Then this is the condition. What is that? You see here. Average load on AC is equal to average load on CB. Then how the average load is defined is load on AC by span AC. So, defined as this way. Average load on AC is defined as load on AC by span AC, like that. Load on AC means you will get W into X is the load on AC by span is A. Load on CB is W into L1 minus X is the load by B. So, we can write it as X by A is equal to L1 minus X by B. If this condition is satisfied, area of the trapezium is maximum, and to get maximum area of the trapezium, the two ordinates must be equal. So, automatically if that condition is satisfied, this ordinate and this ordinate, that means at the ends of UDL, the ordinates will be equal. Only then a trapezium area will be maximum. That is what you have learned in mathematics, 6th or 7th class mathematics, you have studied that way. For trapezium area to be maximum, the edges sides must be equal. Okay. So, now this we will write it like this. Conclusion. If the above condition is satisfied, we get maximum bending moment at C. That means if condition is satisfied, what will happen is the ordinates at the ends of UDL will be equal. So that trapezium area is maximum. That is the first thing. Second point is, this is x by A is equal to L1 minus x by A, L1 minus x by B. What it means is, to get maximum bending moment at any section C, what we have to do? This is ratio of loaded length and corresponding span must be equal, or we can also read that way. whatever ratio C cuts the span AB, it must cut the load also in the same ratio. Either this way we can write it or this way we can write it, both ways. Once they have asked this one, if to get maximum bending moment at any section C, x by A is equal to L1 minus x by B. First you have to select whether it is correct or wrong. Next reason is, if that condition is satisfied, ends of UDL ILD ordinates are equal, ordinates at the ends of UDL will be equal, and area of the trapezium is maximum. Then assertion, reason, both of them are correct, and reason is the correct explanation for the assertion. Like that. Once you understand this one, any question they ask in the exam you can manage. Now let us see how the numericals will come. Let us see a question. A UDL of 5 kilonewtons per meter and length 3 meters crosses a simply supported beam of span 10 meters. Maximum bending moment at a distance of 4 meters from left support. Now you see, if a question of this type is given, this point let us say AB, assume that here there is a ground, it's moving like this point is let us say C. This length at a distance of 4 meters from left support means your A becomes 4 meters, now B becomes 6 meters. So total length is 10 meters. So we will draw first the influence line diagram for bending moment at C. Now that this section is specified, then average load on AC is equal to average load on CB, condition must be satisfied. Okay, this is your ILD for bending moment at C. This value is AB by L. A means 4 meters, B is 6 meters, length is 10 meters. So you will get 2.4 meters. So this height is 2.4 meters. Now you must adjust the load like this. This is 5 kilonewtons per meter and total length L1, let us say 3 meters. And this distance we take it as x. The remaining distance is 3 minus x. Now, this is the condition. Average load on AC is equal to average load on CV, or loaded length by span, corresponding span is equal to loaded length by the other span. So, x by A, x by 4 meters, 3 minus x by 6 meters. So, x you will get 1.2 meters. Now, you see this distance must be 1.2 meters. This is 1.8 meters. Okay. Now, having found this one, 1.2 meters means this value now will become 2.8 meters, because total is 4 meters. This becomes out of 6, 4.2 meters, like that. If you take the linear interpolation, see here, for a distance of 4 meters, it is 2.4 meters. 2.8 how much? For a distance of 4 meters, you have 2.4 meters. For a distance of 2.8 meters, what is the ordinate? 2.8 by 4 into 2.4. So, 1.68 meters. So, this ordinate here you will get 1.68 meters. This ordinate you do not have to check it, directly you can write it as 1.68 meters, it has to be equal. Supposing that you get a doubt beforehand itself, here we will check it, but in the exam directly we should write it to save our time. It has to be equal. Now, you see 6 meters on the other side if you take it, for 6 meters 2.4 meters, for 4.2 meters how much? So, 4.2 by 6 into 2.4, again 1.68. So, like that, if this condition is satisfied, loaded length by span is equal to loaded length by span, or whatever ratio C cuts the span AB, in the same ratio C must cut the load also. Then you will get two ordinates of ILD at the ends of UDL, they have to be equal, and trapezium area will be maximum. So, now this is the condition. To get maximum bending moment at C, keep UDL as shown in figure. So, now maximum bending moment at C is nothing but intensity of UDL into area of ILD under UDL. Why we take area of ILD? Because UDL can be treated as infinite number of point loads. Point load into ordinate, that means point load into displacement, you will get the work done, virtual work done. So, area of ILD is nothing but total virtual work done by the applied load. Okay. Then VA into 1, it has to be 0. So, VA you will get from this one, intensity into area. Okay. So, intensity of load is 5 kilonewtons per meter into area of ILD, area of trapezium. In the area of trapezium, we will calculate like this. First split into a rectangle, this is the rectangle, then triangle. So, rectangular area you will get like this, 1.68 into 3, this is area of rectangle, plus area of the triangle, half, base is 3 meters, total height, now left out height is 2.4 minus 1.68, this is half base into height. This is area of triangle. So, you will get 30.6 kilonewton meter. So, one of the options will be 30.6. Okay, now let us see one question. In the workbook, the 26th problem, 63rd page, there was a question like this. A UDL shorter than the span is moving on the beam. How much of UDL should cross C to get maximum bend moment at C? In the earlier problem also, when you have taken 1.2 meters here, you got it. That means UDL should cross the 1.8 meters in the earlier case. Now, how much it should cross, we will see. We have a UDL length not given, some length was there. This is simply supported beam A, B. This point he says C. He gives you this distance L by 4, then B value will become 3L by 4. Question is, a UDL shorter than the span is moving on a simply supported beam of span L. How much of that UDL should cross C, which is at a distance of L by 4 from left support, to get maximum bend moment at that point? Now you see how much it should cross. Like that it should be there, W kilonewtons per meter. If you take this length, let us say L1, naturally whatever ratio C cuts these two members, these two spans, it should also cut in the same ratio. That means it has to be 3L1 by 4, this must be L1 by 4. So C cuts the span AB in the ratio of 3:1. Then loading, it should also cut the load also in the same ratio, 3:1. So to get maximum bend moment at C, C must cut the load in the same ratio it cuts the span. So, three-fourths of UDL should cross C to get maximum bend moment at C. Like that. Now let us see, this is what they have given once. How much of UDL should cross? In the ESC prelims type examinations, simply they stop here, how much UDL should cross C. But in gate type examination, then what's the bend moment also? As we have calculated in the earlier problem. There also how much should cross C means, we have written total 3 meters length, x value got 1.2. Then the other L1 minus x is 1.8 meters. That means the UDL should cross C by 1.8 meters in the previous problem. So up to how much should cross means you don't require calculator. So quickly you can manage. But the magnitude if you want, you require a simple calculation. Okay. Now let us see, if UDL shorter than the span is moving, this is the case. If more than 2 point loads are moving, this type of exactly equal sign will not, if it happens fine, if it doesn't happen, then what we should do? See, that is, we will take note 3. If more than 2 point loads are moving on simply supported beam, Then to get maximum bending moment at C, keep the loads such that average load on AC minus average load on CB. It should be actually equal or it can be less than also. Once one by one it is crossing. So first preference is it should be equal. If it cannot be equal, next choice is what it will become less than that. That means supposing that you have a span, I explained to you with the help of example. What it means is average load on AC minus average load on CB should be less than or equal to 0 means you have a span say 10 meters. Then at any point C we want to find maximum bending moment. Assume that 4 wheel loads are moving. One by one, once loads enter the bridge, all the loads will be on one span AC. Then average load on AC is maximum. Then average load on CB is 0 because loads are yet to cross section C. Now one by one when they are crossing the section C, two possibilities can happen. Average load on AC can be exactly equal to average load on CB, or depending on the magnitudes of the loads, instead of equal, less than can happen. That's all. So that does not mean that wherever you have less than symbol, you will get maximum bending moment. Once one by one loads are crossing, at one particular load when it crossed, average load on AC became less than. Then one more load crosses, say, then also less. One more load crosses, then also less. Then you don't get maximum bending moment at C for all loads. It should be equal. If equal doesn't happen, the next change of sign is less than. So in the exam, if a question is asked, average load on AC must be equal to average load on CB only is correct one. That only is you have to write. If you say average load on AC is less than average load on CB, let us say, then for all average loads on AC less than average load on CB, that condition must be satisfied. It will not satisfy. So you will not get maximum bending moment. First change of sign, as it should be equal first thing. If that cannot happen, next possibility is less than symbol. Let us see with the help of examples, where we have two examples I will give you, where it will be first problem less than symbol, second problem equal and less than happens, say. First change of sign wherever it happens, you will get absolute, means you will get maximum bending moment at that section. First when loads are moving, first greater only will come. Next one by one when it's moving, equal sign comes, say, you will get maximum bending moment there. One more load crosses, then less than symbol will come. Then you will get equal maximum bending moments under two loads, wherever equal sign happens or less than happens. Two examples we will see. With that, instead of talking whatever we talk it looks vague. When you solve the problem, you will understand what I wanted to tell you. Let us see the questions. For 4 wheel loads, 3 kilonewton, 4 kilonewton, 5 kilonewton and 6 kilonewton, spaced 2 meters, 3 meters and 3 meters apart, cross a simply supported beam of span 24 meters with 3 kilonewton load leading. Which load is leading also they have given? Leading from left to right. So 3 kilonewton load is leading and they are moving from left to right. For that condition only you have to check what is the maximum bending moment at the section C. Otherwise they can move forward, they can reverse the direction, move forward, backward. 4 possibilities we have to check. So to avoid that wasting of time, only one possibility you have to check. 3 kilonewton load is leading and they are moving from left to right. For such cases, what is the maximum bending moment? To get maximum bending moment, at 18 meters from left support, 18 meters from left support, the load that should be placed at the section is. Now options are like this: 3 kilonewton, 4 kilonewton, 5 kilonewton, 6 kilonewton, and these loads are moving like this: 3, 4, 5, 6, 3, 4, 5, 6, spaced 2 meters, 3 meters, 3 meters apart, is moving from left to right. Okay. Now let us see, this is our problem. This point, let us say A, B, somewhere here C is there. This distance A is 18 meters from left support, B naturally will become 6 meters. AB by L. This is ILD for bending moment at C. Now you see, first we will keep the all loads here. All loads will be here. Here 0 load will be there. So we will write this table. Average load on AC, then average load on CB. Okay. First what will happen? Which load will cross? 3, 4, 5, 6 are there. This is how the loads are moving. Here I will write it otherwise. 3, 4, 5, 6. Okay. So when they are moving, first 3 kilonewton load will cross. So when 3 kilonewton load crosses C, then what is the average load on AC? Left out are 6 plus 5 plus 4. 6 plus 5 plus 4 by 18. 11 plus 4, 15 by 18 here. Naturally this value is greater than, now load crossed 3 by 6. This is 0.5, this is more than 0.5. Then ask the driver 4 kilonewton also to cross C. When 4 kilonewton crosses C, 4 also crossed, now you will get 6 plus 5 by 18, 11 by 18. So now this value is less than 4 plus 3 by 6. 7 by 6 means it is more than 1, it is less than 1. See here, less than symbol happened. See, first when 3 kilonewton is crossing, average load on AC is more than average load on C. First more only will be there when they are moving from left to right. Okay, this is greater. Then when 4 kilonewton crosses C, equal sign didn't happen, because magnitudes are such that it can be equal or it can be, next choice is less than. Where that change of sign happens, we have to see. Under that load, you have to keep, you will get maximum bending moment at that section. Mathematical proofs, all the textbooks will give you, but now proof is not required, understanding only is required. For all the cases, proofs, some proofs are useless, means they are necessary conditions but not sufficient conditions. So this is one you have to, it is a necessary condition, also sufficient condition. When 4 kilonewton crosses C, it is less than. That means you have to keep 4 kilonewton at C. Conclusion. When 4 kilonewton crosses C, average load on AC is less than average load on CB. See, whenever if now 4 crosses less than symbol, if 5 kilonewton crosses less than will happen, then under 5 you will not get. First change of sign, it must be equal. If that doesn't happen, less than symbol. That's all. So, wherever less than average load on AC is less than average load on CB, say you won't get it. One by one when they are crossing, it should be equal, otherwise first change of sign. So, average load on AC is less than average load on CB. More precisely, you can write it like this, that is change of sign. Change of sign means greater than symbol to equal symbol is change of sign, or less than is also change of sign. So, wherever change of sign happens, you will get load maximum bend moment at that point. That is change of sign occurs when 4 kilonewton crosses C. So, keep 4 kilonewton at C to get maximum bending moment at C. This is important. Wherever change of sign occurs, first thing is greater will come, then equal happens, then maximum bending moment will come, because change of sign happened. One more load crosses, equal to less than it will become. So, again change of sign. Such cases, you will get equal maximum bend moments under 2 loads. In this case, only one change of sign happened, greater to less than symbol. So, only one point load you will get maximum bend moment. One more load crosses, again less, but it is not change of sign. So, you will not get maximum bending moment. So, you have to keep here 4 kilonewton means 4 is the answer. If you have the prelims type examination where calculators are not permitted, you will be asked to stop here itself. But in GATE examination where calculators are permitted, you must find what is the magnitude of maximum bending moment also. So, supposing that you want to find maximum bending moment, magnitude of maximum bending moment at C is, supposing that if they give like that, now you have to do this way. As you have learned just now, you must keep 4 kilonewton here, already 3 kilonewton just now crossed. So, 3 here, 4 is crossing, now here 5, here 6. This is the position of loading. This is 2 meters, 3 meters, 3 meters. Now, by linear interpolation, you can find this height we know, AB by L. This ordinate is AB by L. A means 18, B is 6, by length is 24. So, you will get 4.5 meters. So, this ordinate is 4.5 meters. Now, by linear interpolation, we can find these ordinates also. See here, this length is now 12 meters only. Here to here 15 meters. This is 18 meters. And here to here it is 4 meters. This is 6 meters. Now, for a length of 18 meters, 4.5. For length of 12 meters, 3 meters. 12 by 18 into 4.5. And similarly here 3.75 meters. And here for 6 meters, 4.5, 4 meters, 3 meters you will get. Simple linear interpolation. Now, maximum bend moment at C is load into ordinate. You see, in this case, it so happened that these two ordinates are equal. Like UDL shorter than the span, area of trapezium when you are calculating, the two ordinates are equal, ends of UDL. In this case also they are equal, but it is not necessary when point loads are moving. They should be equal condition not required. Okay. In this case, it so happened that they are equal, but they can be different also. Now, 6 into 3 plus 5 into 3.75 plus 4 into 4.5 plus 3 into 3. So, this is the maximum bending moment. You will get 63.75 kilonewton meter. So, this if they ask like this means it is in the gate. Stop here itself is in the prelims. Either where calculators are not permitted, which load should be kept at the section to get maximum bending moment at the section. If they don't specify the section C, then we have to select a section. If you have to select a section, you will select near center. Then the bending moment, maximum bending moment, what you get is absolute maximum bending moment. That point we will see later. Now we are specifying the section. So at that section, what is the maximum bending moment? So this is the process. Now in this case, greater symbol when loads are moving one by one, first average load on ES is greater. Once 4 crosses, it became less, but it can be equal also. If equal comes, less than comes, then how the maximum bending moments you will get. Let us see one more example. Now this is 38 by 65 in the workbook. In this case, what he has given is 3 wheel loads are moving. 10 tons they have given, will make it kilonewton. 10, 26, 24. Spaced 2 meters apart. You have 3 wheel loads, 10 kilonewton, 26, 24, spaced 2 meters apart. They are moving from left to right on a simply supported beam of span 20 meters. This is the span, 20 meters. He has given itself. We'll write here. This span they have given 20 meters. So maximum bending moment at a distance of 8 meters from A. This section C has taken. A he says 8 meters, naturally B is 12 meters. Now we have a span, simply supported span AB, whose length is 20 meters at a distance C, which is at a location C at a distance of 8 meters from left support. What is the maximum bending? To get maximum bending moment at C, which load should be kept? When the loads are moving from left to right, they are moving left to right. Direction given, loading is given, This is leading. 10 kilonewton load leading. So 4 options were given. 10 kilonewton should be kept at C, or 26, or 24, either 26 kilonewton or 24 kilonewton. These are the options. Let us see what happens. Average load on AC, average load on CB. Okay, first which load will cross? Say 10 kilonewton crosses C. When 10 crosses C, what will happen? What is the left out here is 24 plus 26 by 8. That means 50 by 8. This is greater than 10 by 12. Next, second possibility, 26 kilonewton crosses C. When 26 kilonewton crosses C, how much is left out now? Here left out is only 24. 24 by 8. Here 26 plus 10 by 12. This is 3. This is also 3. So in the process, what happened here is this is 3, this is 3. So both are equal. First greater than symbol was there. Now greater became equal. So change of sign happened. So maximum bend moment will happen at C. Supposing that if 24 kilonewton also crosses C, when 24 kilonewton crosses C, what's average load now here? 0. Now here 24 plus 26 plus 10 by 12. Okay, now what happens here? Is equal to symbol change to less than. 0 is less than this. So first change of sign happened here, second change of sign happened here. That means you will get 2 equal maximum bending moments under 26 and also 24. If this equal is not there, say, then greater to less than happens. Only one change of sign. So only under only one load, whatever load it changes its sign, there it will happen. So your conclusion is like this. See, answer here is either 26 kilonewton or 24 kilonewton is more correct. 26 you will get correct, 24 also will get. But out of these 3 options, this is more correct because both conditions it satisfies. Under either 26 or 24, you will get maximum bend moment at C. So if you draw the bending moment, ILD for bending moment, say, let us see what happens in such cases. If you draw the ILD for bending moment, it works something like this. Here I will explain that part. What is happening in this case? Supposing that this is our beam. Whenever equal sign happens, this is what is going to happen here. See, this is A is 8 meters, B is 12 meters. Next, AB by L means it will go something like this. In the exam, you cannot afford to check this one. Mathematical proofs are not required. Any textbook if you open, they will give you under what circumstances you will get maximum bending moment. The proof we are leaving it, we are taking only the likelihood examples. Otherwise, proofs also if you have to give means it will take 100 hours for each and every case. So ILD for bending moment at C is this one, AB by L. A is 8, B is 12, C, L is 20. So you will get 4.8. So this height is 4.8 meters. Now you see, when the loads are crossing, equal sign happened, exactly equal. So this is the first possibility. This is how much? 26 kilonewton. This is 10. This is 24. Supposing that they ask you here, maximum bend moment at C is, they ask say. Question happens to be like this. Now you see, this is 2 meters, 2 meters. Now this value now becomes 6 meters. For 8 meters, 4.8 means 8 into 6, 4.8. So 6 into 6, 3.6 meters. Now you see, for 12 meters, 4.8, that means 12 into 4 is 4.8. Now this becomes now 10 meters. So 10 into 4, 4 meters, for like this. So 12 for the 48, 10 for the like that. That ratio is 4 here. So 10 into 4 you have to write. So max, this is first possibility. In this case, bending moment at C is 24 into 3.6 plus 26 into 4.8 plus 10 into 4. So you will get 251.2 kilonewton meter. Now assume that the load crosses. Ask the driver to move forward, then 24 will come like this. This is 24, this is 26, this becomes now 10. This one. So now this becomes 8. 8 into 4, 3.2 meters. This is your second possibility. Now you see bending moment at C. You will find that 24 into 4.8. Now you are taking, this is 24, 4.8, 26, 4, 10 into 3.2 plus 26 into 4 plus 10 into 3.2. You see, exactly you will get same 251.2 kilonewton meter. So whenever equal sum sign happens like in the earlier problem, you will get equal maximum bending moments wherever that load changes, or whenever load passes, wherever change of sign happens. First greater will come, then one by one when they are crossing, two possibilities, equal or less. If equal comes, equal and less than symbol, both cases two same maximum bending moments will get. If equal is not there, only one load you have to keep it, wherever that change of sign happens, greater to less than happens, then only under that load you have to keep under that load you will get maximum bending moment. So two possibilities can happen such cases. So both you have to remember. Is it directly changing its sign from greater to less than or greater to equal to less than? Such cases you will get two equal maximum bending moments. Then this calculation, if at all it is the prelims say, you cannot check whether they are equal or not and waste the time. They have to be equal. So in this way. Now after confirming this, in the exam if the question comes, either or you have to answer, either 26 or 24 kilonewton. Now, let us see the fourth point. Now, we have seen in the bend moment different cases, UDL longer than the span, UDL shorter than the span, or 2-point loads or more than 2-point loads, how that average load on AC is equal to average load on CB. These cases, section is specified. If the section is not specified, then you have to select the section also. Such cases, the bending moment that you get is called absolute maximum bending moment. Then how they ask such questions, let us see. Okay, note 4. When a series of wheel loads are moving on a simply supported beam. You see, we are discussing only simply supported beam cases till now. ILD for reaction, ILD for shear force, ILD for bending moment for simply supported beams. After this, we will see the cantilever beams also. Moving on a simply supported beam, comma, to get maximum bending moment under a chosen wheel load, keep the loads such that the chosen load and the resultant of load system are at equal distance from center. Then maximum bending moment occurs under the chosen load, but not at center. Now, in this case, you want to get maximum bending moment under a chosen load. Then that load and the resultant of the load system should be equal distance from the center. Then maximum bending moment you will not get under the resultant or at center, you will get under the chosen wheel load. Okay. So, maximum bending moment under chosen wheel load but not at center. The meaning of why so carefully we have to adjust the loads, that comes from our strength of materials only. With the help of numerical, I will explain what happens in this case. See here, a train of 2-point loads of 150 kilonewton and 100 kilonewton spaced 5 meters apart crosses the beam shown in figure from left to right. With 100 kilonewton load leading. So, which load is leading also he has given. Maximum sagging bending moment. This also you have to remember. We wanted maximum sagging bending moment which may occur anywhere. Which may occur anywhere in the beam is. This is the problem. The points that you have to remember is, he didn't give you the section where you want to get maximum bending moment. That means you have to select section near center. Such cases, the resultant of load system and the chosen load. Chosen load, in this case, he gives you 150. If load he doesn't choose, then we have to choose the load also. Which load you get maximum bending moment. Okay. So, that case, so we have to choose the load, we have to choose the section, then which may occur anywhere means that is the meaning of that. Wherever you want you find it, but I wanted maximum bending moment, which we call it as absolute maximum positive bending moment in this case. Okay. Now, let us see, these are the points you have to get it. This is for our understanding only. What are the things that we have to observe when you are solving the problem in 2 minutes time? We don't have to write this note in the exam. This is for our understanding only. First point, in this problem, the section of the beam is not given. Section of the beam is not given. So, we have to choose the location. So, we have to choose the location of maximum positive bending moment. So, maximum bending moment, maximum positive bending moment occurs near center. This is what we have learned in strength of materials also, near center. Even for UDL also, what we have learned was, I told you earlier case, these load should be adjusted such that average load on A is equal to average load on CB, that x by A is equal to L1 minus x by B. In strength of materials, what you have done, what they give you is one simply supported beam. I will explain here. This again will cut it. I want to find A, B, C, let us say some load was there. This distance is x, okay. This length is say A. This is what they will give. Without average load wording, what you have learnt in SM is simply supported beam, length L, load length L1. Then at C, left of C, there is x distance. What is the value of x to get maximum bending moment at C shown in figure? For that, what you have to do? Take this x as it is. For this condition, what is VA? You will get in terms of x. Then find bending moment at C. VA into A minus Wx square by 2. For that bending moment to be maximum, then dmx by dx is equal to 0. Then find x. And x value you find that x by A is equal to L1 minus x by B. There you have done mathematically, you have proved that how it comes. Now we are simply observing that load by whatever ratio C cuts the span AB, it should cut the load also same way, because every time you cannot derive it and waste our time. First you will derive, observe it. Those observations we have to use in the exam. Okay. Now section specified is one thing. In this case, section is not specified. So we have to choose the section, and that section is near center. Then second point you should get is, to get maximum bending moment under a chosen load. Under a chosen wheel load, the resultant of load system, this is the condition I have given, the resultant of load system and chosen load must be at equal distance from center. Immediately, since he didn't give the section having observed, then this is the condition you should get it. Then how to get maximum moment? So load and resultant must be equal distance. Then how to find the resultant? Third point, to locate resultant, this is engineering mechanics problem. First year engineering mechanics you have done. To locate resultant, use Varignon's theorem. What is Varignon's theorem? That is moment of a force about any point is equal to moment summation of its components. Its components about the same point. This Varignon's theorem, in our civil engineering applications, we have applied two places: to locate the line of action of the resultant and to find the centroid of a line or centroid of area or centroid of volumes. So, to find the centroids and to find the line of action of the resultant, we used Varignon's theorem in your first year engineering mechanics, and thus that concept we will take it to find the location of the resultant. See here, this is what we have done in first year. This is 100 kilonewton. This is 150 kilonewton, spaced 5 meters apart. This point, let us say A. The resultant will act somewhere here. This is the line of action of the resultant. What is the resultant? Summation of the forces 150 plus 100. Now, where it will act? Assume that it acts at a distance of x bar. So, moment of a force about any point is equal to moment summation of its components. So, taking moments about A. So, R into x bar, see where it is not in equilibrium. So, R into x bar is equal to 100 into 5 plus 150 into something like that, we should not do. These two systems, 150 and 100, two forces are not in equilibrium is the first understanding. We only want to find, or we want to replace this two forces system with a single force system. Then moment of this resultant about any point R into x bar must be equal to moment summation of its components, because R is nothing but 150 plus 100. Whatever moment R gives, 150 plus 100 also should give the same thing. So, R into x bar is equal to 100 into 5, okay, plus 150 into 0. So, R we know 250 kilonewton. So, from this x bar we will get 500 by 250 is 2 meters. Okay. So, now we know how to, where the resultant is acting. Next. Now, the fourth point is the problem. Now, I remove this. This is only our understanding. Now the problem comes. This is 100 kilonewton, 150 kilonewton. The resultant is acting at a distance of 2 meters. Now this system must be kept on the beam like this. This problem they have to give us. Let us say this is P, Q, R, S. This length is 3 meters, 10 meters, 5 meters. Okay. This load system is moving on this beam. We have to visualize here also that there is a ground. When it is moving from the ground to the bridge to the ground, what is the maximum positive bending moment you may get anywhere in the section? Sagging bending moment he is asking, not hogging bending moment. Hogging bending moment means negative bending moments. They will occur at somewhere R, support R. At the overhang portions you will get maximum negative bending moment. That maximum negative bending moment value may be more than maximum positive bending moment, we do not want to know. We want only what is the maximum positive bending moment. Then you must understand where you have to keep the loads to get maximum positive bending moment. Then strength of materials will tell you in a simply supported beam, in the supported span only you have to keep the load, then only it will sag. If overhangs portions you keep the loads, it will hog. Okay. So you must keep in the supported span. Now you should get the idea. It is like a simply supported beam. For simply supported beams only that conditions are applicable. Now you select the center C. This distance is 5 meters. This is also 5 meters. Whether overhang lengths 5 meters are there, 6 meters are there, 7 meters are there, we are not interested because it will sag here only. Now take that load system, stick it here. How you have to stick it? Load, the chosen load, 150 kilonewton and the resultant. They should be at equal distance from the center. Now this distance we know 2 meters. This is now it has to be 1 meter, 1 meter, 2 meters gone. Then another wheel load is 100 kilonewton. This point I can take say D, E. Now you will not get maximum bending moment at center or under the resultant. This resultant is only an imaginary line of action of the load. In strength of materials you have studied when you are doing the bending moment diagrams for the point loads. Under the point load, any point load only you will get bending moment. Change of slope happens only under point load, not in between. So here there is no load, so you don't get maximum bending moment under imaginary line of action. Neither at center because there is no load also. So you will get absolute maximum positive bending moment under 150 kilonewton load when this is at a distance of 1 meter from left support, 1 meter from center. So this point, now let us see. Now this distance we take it as say A. A now becomes 4 meters, this becomes B, 6 meters. Okay. Now this overhangs, now we are not interested in this. Now you are drawing influence line diagram for bending moment at D, not at center. So at D only. Without remove, what is the ILD for bending moment at D? Without removing the supports at Q and R, assume an imaginary hinge at D and lift it by an amount of AB by L. Then theta becomes 1. In other words, assume an imaginary hinge at D and apply unit rotation. To apply unit rotation, the beam must be lifted by an amount of AB by L. First, this point we will write it. This is AB by L. Up to this we know how we have to write it. If at all I lift it here, this portion, see this is the support is at R, let us say, this point let us say D. When I lift it up like this, D, R is here, this S naturally R and S will go down because D to S is single beam. When I lift it, it will go down like this. So, if overhang is there, extend the line, not there, stop here itself. Like this it will go. Here also the same. Extend the line. This is minus, plus, minus. Okay. Now, this height is how much? AB by L. This is influence line diagram for bending moment at D, but not at center. This is for us to remind ourselves that we are not getting bending moment at center when 2 point loads are moving. It's like a simply supported beam, 2 loads are there, say, it's not necessary that exactly at center. 2 loads location you can adjust it to get maximum bending moment. There in the strength of materials, what you have studied was some locations they give us. Then you draw a triangular trapezium. Now we want to know how to keep the loads to get maximum bending moment. So you have to adjust the loads like this. So AB by L. How much is that? AB by L. A means 4 meters, B is 6 meters. Length is only 10 meters, 18 meters we should not write because the overhangs are useless. Whether 5 meters are there, 50 meters are there, it doesn't matter at all. So when you are assuming hinge and lifted, only this matters. So you will get 2.4 meters. So this height is now 2.4 meters. Now this distance is 6 meters. Now this, there is one more load here, this ordinate, this length is only 1 meter. Because to 6, this space is 5, then this length is now only 1 meter. For 6 meters 2.4, for 1 meter how much? 2.4 by 6, 0.4 meters. Now you will get absolute maximum bending moment, maximum sagging bending moment at D. You will get 150 into 2.4 plus 100 into 0.4. So you will get 400 kilonewton meter. So one of the options will be 400. Now, you may get a doubt that why I should keep a 1 meter left side. I want to keep the load at center, say. Supposing that if we keep load at center 150, then where will be 100? Again that also will move right side. So it will become exactly at the support. This is at center. Then WL by 4 only you have to write. So 150 into 10 by 4. So how much you will get? Around 375 kilonewton meter. But 400 is more than 375. So that's why that 150 should not keep at center, should shift it by a distance of 1 meter. Then what you get is absolute maximum positive bending moment. Wherever you keep the load here, you will not get more positive bending moment than this. You may get more maximum negative bending moment, we are not interested. Maximum sagging bending moment magnitude is this one. How to get maximum negative bending moment? That you have to keep in the overhang portions. That overhangs behave like a cantilevers. So cantilevers we will study again. Then we see how to draw the ILDs for bending moment for cantilevers. So one paper they asked like this. Another paper what they have done was, you are given a simply supported beam, say of span 10 meters, no overhangs, but its section modulus is given, say 400 into or 4 into 10 to the power of 6 mm cube. Then what is the maximum bending stress developed in the beam? Then what we have to do? Then first position the loads to get maximum bending moment. Once you know bending moment, you can find M by Z, then it becomes pure strength of materials. So, bending stress is m by z, that we have to use it to get the bending stress. Sometimes they ask you strength of materials and structures together. For that matter, after these chapters are over, when you are studying the SFBM diagrams for simple cases, instead of solving the strength of materials approach, check whether you can draw ILD for that particular quantity and solve the problem quickly. You will find that if you take ordinary method, if it takes 2 minutes time, if you draw ILD, find the shear force or bend moment, it hardly takes 30 seconds, maybe less than that. So much time you can save if for simple cases where you can find easily ordinates. So, using influence line diagrams will save a lot of time. We will see some of the problems how we must use the influence line diagrams. Though they do not specify use ILD, still we use ILD and get out of the problem fast. Okay. Now you see, in this case, if they give you what is the bending stress they want you to find, say. In the above problem, if section modulus of beam section is 4 into 10 to the power of 6 mm cube, maximum bending compressive stress at top fiber why they have to give top fiber of the beam is if negative bending moment is more than 400 say, then bottom fiber you will get maximum bending compressive stress which may be more than that. That means to avoid that complication they give you bending compressive stress at top fiber. Top fiber bending stress happens only when it sags, right? So, in other words, they are asking you to calculate what is the maximum sagging bending moment, then bending stress. So, you will get this value now. F is now bending stress is nothing but m by z, m 400 kilonewton meter, that means 10 to the power of 6 Newton mm by section modulus is 4 into 10 to the power of 6 mm cube. So, you will get 100 newtons per mm square. Okay. This is how the 2 marks questions come. So, now we will see the cantilever beams. Now, we will see the influence line diagrams for the cantilever beams. Assume that we have a cantilever beam A, B, whose length is say L. For time being, assume that we have a ground here. Okay, unit load, it has no unit, simply one is moving from B to A. Initially, when the load is on the ground, no issue at all. Supposing that if it comes, enters the bridge here. Now we know what is the reaction. VA is equal to 1. If the load comes here, also VA is 1. If load comes here, also VA is 1. That means for all positions of moving load, reaction will not change. That you get it from strength of materials. So wherever load is there on the cantilever beam, you get a same value 1. That means the influence of unit load is constant. Wherever unit load is there, its influence on VA is same, 1. That means your influence line diagram must be a rectangle like this. One here. This is your ILD for vertical reaction at A. Right? So when load is 1, load is here, its influence on VA is 1. When it is here, his influence on VA is again 1. When load is here, say, his influence on VA is again 1. That means your influence line diagram looks like a rectangle. Next, ILD for shear force at RHS of A. Here I want to draw ILD for shear force A. Exactly under point load, shear force is not defined. That means if at all shear force is acting over a load is acting over a very small area, say, in that small zone, shear force changes from positive to negative like that, and it varies like a hashed line. But because that area is very small, you simply draw a vertical line. That's all. But exactly under point load, shear force is undefined, and in other words, shear force is indeterminate. Because even it is acting over a small area, over width of say 5 mm. When you are taking a section, you are taking it 4 mm or 3 mm or 2 mm or 1 mm, you don't know. Simply cut like that means where is that cut section? Over a bearing plate width, which width you have taken? Since it is not clear, so we take it as if it is undefined or it is indeterminate. So that's why we needed to find shear force at RHS of A, but not at A. So let us see how to find ILD for shear force at RHS of A. What's the condition you have done in strength of materials? If I want to draw ILD for, or if you want to find shear force at RHS of A, stand there at RHS of A. Now you have a choice to look left or right. Let me see left side. Don't want, you can look right side. Section left side, upward force VA, positive. Wherever unit load is there, VA is 1 only. That means shear force at RHS of A is nothing but VA. That means shear force is also a rectangle. So you will get ILD for shear force at RHS of A as a rectangle like this. Positive. This is 1, here also 1. This is ILD for shear force at RHS of A. Next, this is ILD for VA. Next, we want to draw ILD for bending moment at A. Reference line. When the load is here, his influence on bending moment at A is maximum. How much? Downward forces always give negative bending moment. So minus 1 into L. So 1 is already there. So influence is minus L. So load into influence, if you multiply, you must get the bending moment at A. As he is moving towards this support, his influence on bending moment at A will be less. If load is at center, say 1 into L by 2 only. When load is here, bending moment at A is 0. So when load is here, his influence on bending moment at A is 0. Here it is maximum. So it will go like this, minus. This is ILD for bending moment at A, or we can say bending moment at RHS of A, because bending moment at A there is a couple MA is equal to W into L or 1 into L. Exactly under couple, bending moment is indeterminate or undefined, we can say. If there is a couple, you put your leg on that itself, couple itself say. Under your leg, M is there or 10 M is there, you cannot see. So that's why wherever there is a couple, strength of metals you have studied, left side of the couple you find bending moment, right side of the couple you will find bending moment. Okay? Because under the couple, bending moment is indeterminate. So we have to find, but we say as if it is bending moment at A itself, because RHS of A and A, there is no much difference. So we write as if like this. But to be more clear, it is bending moment at RHS of A, because there is a couple at A. So now ILD for bending moment at A also we have written. Now let us see this problem, reaction, shear force, bending moment. Now quickly we could manage. But in the exam also you see, to find ILD for VA, first I kept load here, then here, then here, 3 places I needed to find. But if this cantilever beam is attached to another simply supported beam, say, with a pin linking, then this analysis, if load is on the other portion of the beam also, you cannot find reaction like this and draw ILD. It takes 3 minutes time. So we have to take the help of Muller to find the influence line diagram. Like simply supported beams, here also we will take the help of Muller's. Otherwise, we cannot find in the stipulated 1 minute time or 30 seconds time. So this is what we have given. First point is ILD for vertical reaction at A. From strength of material, this is what you have written. For all positions of unit load, VA is equal to 1. So draw ILD as a rectangle as shown in figure. But this much we cannot do from Muller. What we can do is, as in the simply supported beams case, you see here, this is what you have done. You have a simply supported beam A, B. To draw ILD for VA, what you have done? Remove the support, lift it by 1. Then the deflected shape gives you ILD for VA. That's how it deflected. Now here there is no moment. So we didn't release the moment, already moment is 0. Same process here you see. We have a cantilever beam like this. There is a moment here, reaction here. If I want to draw ILD for VA, release only VA. Don't release the moment. As in the simply supported beams, here also, keep the moment as it is, only release VA. So without releasing the moment, remove the reaction and lift it by 1. Then the deflected shape of the beam itself is the ILD for VA. If at all you release the moment also, then it will fall down like this. It will. So we should not release the moment. Without releasing the moment, hold it tight, don't release the moment. Now you can lift it like this. Then it will take a rectangle shape. Releasing the moment means you put pin also like this. 2, if you release, it will fall down. So to draw ILD for VA, you have to do like this. This is a process. Without removing fixed end moment at A, remove the reaction at A and apply unit vertical displacement Then the deflected shape of the beam, itself is the ILD for VA. Next, second one. ILD for shear force at RHS of A. Again, strength of materials process is like this. For all positions of unit load, shear force at RHS of A. How will you find? You stand at RHS of A and look left. This is the process. Wherever you want to find shear force, stand there. Now you have a choice to look left or right. In this case, we look to left. So stand at RHS of A means here. Look left means this one, VA. Don't want, if you look right side also, one down will be there, that's all. You will get plus VA. So, draw ILD for plus VA. It is the ILD for shear force at RHS of A. At RHS of A also. But this much only for one point, one cantilever is there, we can manage. If cantilever is attached to some other beam, this way you cannot find it. So molar. Now what we have to do? Okay. Now you see, in this case, first as a reference line shear force, we will take up this point A, B, this point let us say C. What you have done for shear force at C? Without removing the supports at A and B, cut the beam at C and lift the beam at C such that left piece I have to push it down, right piece I have to lift it up. This is what you have done. Minus plus. Okay. So the total ordinate here is 1. This is theta A. This is theta B. This is what we have studied. Now same concept we try to apply here. Without removing the support at A, cut the beam at RHS of A, because you want to find at RHS of A. Now that small piece is there. You try to rotate. You can't rotate that because it's a fixed one. So in a cantilever beam is also a statically determinate beam. Cutting the beam implies that it becomes unstable. Then no rigid body, only rigid body rotation or translation should happen. No deformable rotation should be there. Since that small piece is not rotating, don't forcibly rotate. Leave that piece off. Then right portion. See, after cutting it, right portion you have to lift it up. Why you should lift it up? Then only it will satisfy your already learned shear force sign convention. From shear force sign conventions only lifting up down came. So, see, when this is not going down, total ordinate must be 1. So, after cutting it, without removing the moment, whatever moment that exists here when far end is free, then total ordinate should be 1, push it by 1. Then the deflected shape of the beam itself is the ILD for shear force at RHS of A. So, this is what Muller said. Without removing the support at A, cut the beam at RHS of A. Without removing the moment, hold the beam and apply unit displacement. Then the deflected shape of the beam itself is the ILD for shear force at RHS of A. If you release the moment again, it will fall down. Only one shear force only you have to release. If already moment is existing, don't touch that. Okay. So, this is what we have to do. So, without removing the support at A, this is the process. Without removing the support at A, cut the beam at RHS of A. Cut the beam at RHS of A. So, without removing the moment, apply unit displacement. Apply unit displacement for the beam. For the beam at RHS of A. Why? Left beam is not moving, left side of cut section, so don't force it to rotate or to translate. So, you have only this choice, apply unit displacement for the beam at RHS of A. Then, the deflected shape of the beam itself is the ILD for shear force at RHS of A. Next, ILD for moment, let us see. I remove this part. ILD for bending moment at A. See, first point is when unit load is at B, bending moment at A is minus 1 into L from strength of materials, because downward loads will give negative bending moment. So, minus is because of that into L. What it means is, it means that the influence of unit load on bending moment at A is minus L. That is the meaning of minus L. Influence of load is minus L. Now, when unit load is at A, what is the bending moment at A? 0. So draw ILD. Draw ILD as a triangle. As a triangle as shown in figure. But for simple case itself, 2 times we need to write. So what Muller said we have to see. First point is characteristics of ILD for bending moment at A. You see now, coming to this problem, if I take this one, what is theta A here? You see you rotated clockwise. Whether you rotate clockwise or anti-clockwise, the downward load should give negative bending moment, that's all. So theta A, how much is that? L by L is 1. This L, you should not take tan theta A is equal to L by L is equal to 1. So theta is equal to 45 degrees, we should not write. Because it's not a real displacement L, it is a virtual, means an imaginary length L, that's all. Okay. So tan theta A is approximately theta A is equal to L by L is equal to 1. From this understanding, what Muller said was, as in the case of this one, you have a simply supported beam. I want to draw ILD for bending moment at C, say. What you have done? Assume an imaginary hinge and apply unit rotation. To apply unit rotation, what you have done? You lift it by an amount of AB by L. So that this theta I want 1, say. For theta to become 1, I have to lift it by an amount of AB by L. Assume a hinge, lift it by AB by L, then automatically theta becomes 1. That's what you have learned. Unless otherwise you lift it by AB by L, this type of rigid body rotation cannot take place in simply supported beam. Come to cantilever. Without removing the support at A, assume an imaginary hinge there. Because you didn't remove the support reaction, beam cannot be lifted because reaction is holding him. So you have to keep the beam there only. Without lifting also I can get unit rotation. See like this. This is the cantilever beam, fixed is there. Without removing the reaction, assume a hinge there now. That means hold it like this. Don't give 360 degrees rotation, only unit rotation like this. Then the deflected shape of the beam itself is the ILD for bending moment at A. So this is the process. Without removing the support at A, assume an imaginary hinge. Assume an imaginary hinge at A. Assuming an imaginary hinge means releasing the moment, that is, release the moment at A and apply unit rotation. Muller will not tell you to rotate clockwise or anti-clockwise. It is our choice. Depending on already learned bending moment sign conventions, since we know that downward loads will give negative bending moment and beam should deflect downwards, then only you write it as negative. So your theta A happens to be clockwise, but it can be anti-clockwise also, because supposing that I have a cantilever beam like this, I need not put always like this. This is AB. Now assume an imaginary hinge. Now how to rotate? You see, it must go down only because due to the load, I must get negative bending moment only. So like this. So this is one. Now you see, you rotated anti-clockwise. So clockwise or anti-clockwise, but beam should go down. To tell you that means from strength of materials, you must have an idea that due to downward load, cantilever beam produces hogging bending moment. In the cantilever beam, there will be hogging bending moment. So it should go down only. So either clockwise or anti-clockwise, let the beam go down this way. Release the moment at A and apply unit rotation. Then the deflected shape of the beam. Deflected shape of the beam itself is ILD for bending moment at A. Like that. Now we will see the numericals on the cantilever beams or overhang portions. ILD for bending moment at A is now we have a cantilever beam, also overhang A, B, C, D, let us say. This length you assume that it is 3 meters, 2 meters and also 2 meters. A cantilever attached to another member. Finally, it is statically determinate structure only. This is internal floating hinge. Internal floating hinge. Now we are asked to draw ILD for bending moment at A. Okay, ILD for bending moment at A means first you assume that BCD portion is not there. We know how to manage the cantilever beam AB. Okay, because it's a fixed support, at the support only we want. Whenever you want to find bending moment at this ILD for bending moment at the support only, we should not lift it or we cannot lift it because reaction will be there. Reaction we should not touch, only moment I have to release. In the process, the reaction is holding the beam. So you should not lift it. Keep it there only and apply unit rotation. You apply unit rotation such that the beam goes downward. Why should it go downward? Is downward loads will give downward moment only. Downward load should give negative bending moment only. So this is the process. ILD for bending moment at A. What we have to do? Without removing the supports at C and A, assume an imaginary hinge at A and apply unit rotation. Without removing the supports at A and C, apply unit rotation. Apply unit rotation at A. The deflected shape of the beam itself is the ILD for bending moment at A. Now you see, don't remove the support at A, assume an imaginary hinge and apply unit rotation. BCD is not there. So it will go down like this. Clockwise rotation. This theta A must be 1. If theta A is 1, this can easily go down. This downward displacement is 3 meters. Okay. Now how BCD you attach it, say. This is the BCD member. This edge you take it as a B. Where I am holding the duster with my fingers is a C. This is the free end D. B can go down because it is a floating hinge. So when B comes down, you see we are not bending or breaking the member. BCD is a single member supporting either like this way roller is there, or you weld it, then triangular plates will be there. So, it can move like this. Okay. So, if B comes down like this, so B to C to D straight, it will go up like this. Okay. This is how the deflected shape of the beam will run. Now, this height is 3 meters because r theta 3 into 1 3 meters. Now, similar triangles come from these triangles. This length is 2 meters. For 2 meters length 3 meters, this is also 2 meters, so it has to be 3 meters. Which means that if this is theta, it can't be theta, it is some other angle alpha. 2 alpha is equal to 3, like that. So, this is negative, this is positive. Once it is given as a 6 marks question in the civil services exam, if it is a 6 marks question, you must explain how it comes. If it is a 2 marks question, you do not have to explain this part, directly draw this diagram. One of the options you take it, that is all. Hardly takes 30 seconds time to read and to check which option is correct. Okay. Now, next one. Let us see the next problem. Find bending moment at A for the beam shown in figure when it is subjected to a UDL of 10 kilonewtons per meter throughout its length. This is the problem. There is a hinge here, support, roller support, one more hinge, one more support. This point, let us say A, B, C, D and E. Everywhere all the lengths are 2 meters and it is subjected to UDL throughout its length. So, he did not ask in this problem that you draw ILD, simply is asking bending moment at A how much. You have a statically determinate but a continuous beam. If you do not get the idea of drawing ILDs, then what you will do is, first you have to find the reaction at E, VE. How? Bending moment at D is equal to 0. So, VE into 2 minus this load is say 10 kilonewtons per meter. So, 10 into 2 into 2 by 2. So, VE will get. Then to find VC, find bending moment at B is equal to 0, then VC will get. Then you will get bending moment at A. So much time waste. Calculations you have to make it so much. So, even if they ask you a question on strength of materials also, you find bending moment or you find shear force or you find reaction in determinate structure, draw ILD and finish off the problem quickly. How to draw that? This is ILD for bending moment at A. Process I told you already, without removing the supports at A, C, E. Assume an imaginary hinge at A and apply unit rotation as in the earlier process. Now the process I am not writing. When you are assuming an imaginary hinge and apply unit rotation, it will take up this position. This theta A is equal to 1. When this goes down, earlier problem, this problem, what is the difference? Earlier problem I stopped here only, right? Now I have extended one more link. Other than that, earlier and this same. So up to here we have already drawn. Like this we have drawn. Earlier problem was up to here. Now what else extra is there is DE portion. Now once it goes up, this has to come down. This is plus, this is minus. Okay. Now what are the, this is 2 meters let us say. So this height is 2 meters. Now all lengths are same, so it has to be also 2 meters. Now you see, what is the bending moment at A? Bending moment at A means intensity of UDL into area of ILD under UDL. Now intensity is 10. This is negative area, this is positive area. What is the net area? 0. So directly you can write 10 into 0, 0 itself. For that you don't have to write this also. Just by saying intensity into area, positive area, negative area are same, net area 0. We can take answer it as 0 itself. So that means having understood that ILD will save our time based on the description, first assume a hinge, draw ILD and check how much it is, that's all. So 10 into, if at all areas are different, we could have written like this, half, base is 4 meters, height is 2 meters. Negative area plus positive area, half base into height. This is negative area, this is positive area. In this case they are equal, so sum became 0. If they are not equal, then net value, some value you will get. So this is once they have given in a gate paper for 2 marks question, what is the bending moment at A? It hardly takes 20 or 30 seconds time, but you should get the idea of drawing the ILD. Okay. Now, let us take some other question on this one. Having drawn ILD for bending moment at A, now we will see how to draw ILD for reaction at C. Reaction at U, we know lifted means only small triangle you will get. I think this we can remove. Same problem, we will draw ILD for reaction at C. Influence line diagram for reaction at C. What is the process? Without removing the support at A and E, remove the support at C and apply unit displacement. Then the deflected shape of the beam itself is the ILD for VC. This is the process. Without removing the supports at A and E, remove the support at C and apply unit displacement. Deflected shape of the beam itself is the ILD for vertical reaction at C. Now you see, without removing the support at A and E, at A we have a fixed support like this. Now can B go up or down? Once I fix it here, if B has to go up like this, say, then I have to bend this one. A curved member you will get it, because I am fixing it here, deflection is 0, slope is also 0. With 0 slope here, it cannot be lifted. Your lifting means it will take a curved portion. But in a statically determinate structure, influence line diagrams are straight lines, because if you remove the support here, it becomes unstable structure. When you displace it, it will only undergo rigid body translation or rigid body rotation, means straight lines only. As a mechanism, it will displace. So, once I fix it here, it has no choice, it will not go up or down. So, having understood that point, this point where I am holding is B, this point is a C, the end point let us say D, and here one more hinge is connected to E. Okay, B, C, D. At C, I am now removing the support and applying unit displacement like this. So, B to C to D, straight it will go up like this. Now, here this displacement is 1. For 2 meters 1, for 4 meters it should be 2. Then it has to come down. This ordinate has to be 2. Now, this is your influence line diagram. At later stages, if you get a doubt how it has come, read this one. Without removing the support at A and E, remove the support at C and apply unit displacement. Then this is the deflected shape of the beam as a rigid body translation. Supposing that at B, if you lift it up, supposing that, then what will happen? Like this it will come. So, curve not possible. So, this we should not do it, only this way it will go up. Now, you see, in one paper they asked a question like this. Reaction at A due to 20 kilonewton at F is like this they have given. This point let us say A, B, C, D, E. Somewhere here there is a 20 kilonewton load. Location also is not given. Somewhere at that point. Let us say 2 meters, 2 meters, 2 meters, 2 meters. Now, you should not calculate reaction at A means first VE, then VC, then sigma y0, then VA you will get. It will take say 2 minutes time. But if you draw ILD, you can complete in 30 seconds time. Now, let us see how to draw ILD for VA. Same as this one. Without removing the supports at C and E, and also moment at A we should not remove. This is a process. Without removing the supports at C and E and fixed end moment at A, comma, remove the support reaction VA or simply support reaction at A and apply unit displacement. Deflected shape of the beam itself is the ILD for VA. Now you see, C and E we should not remove the supports. At A fixed end moment we should not touch it. Now without removing the fixed end moment, just remove the support and lift it by 1. You assume that BCDE is not there, only this is like a cantilever because it's going up and down freely. So apply unit displacement here, 1, don't move it here, don't move it here. So don't remove the fixed end moment. So at A, without removing them and lift it, it goes like a rectangle, like this. Now this point is over. Next C point is here, B is here, C here, D here. If B goes up like this, B from here it is going up, so B, C, D its right goes down like this. B, C, D. Floating hinge is there. Then this will go up. It has to go up only like this. So this is positive. This is negative. Similar triangles, if this is 1, from here to here it is 1. If this is 1, similar triangles, it has to be 1. Now you see, between A and B, wherever this 20 kilonewton load is there, whether here or here or here or here, VA is 20 only. So VA, what is the ordinate here? 1. So VA is equal to 20 into 1. In 2 minutes time, our task is to draw this ILD and get this value. Okay. Now we will see how to draw ILD for shear force at LHS of C. Same problem we will take. ILD for shear force at LHS of C. Floating hinge. Okay, this point fixed support A, B, C, D, E. Same distances. Two meters. This is ILD for shear force at LHS of C. Now, if you want to draw ILD for shear force at LHS of C, what is the process? Without removing the supports at A, C, E. Don't remove the supports. Only when you are finding the reaction, you have to remove the reaction and lift the support by 1. Other cases, no question of lifting the supports. So, without removing the supports at A, C, E, where we should cut? LHS of C. Now, once you cut it LHS of C, this cut is there in the BC span. Now that BC span, how it behaves you have to see. Will it behave like a cantilever or will it behave like a simply supported beam? Now you see, can B go up and down when you cut here? Because of this fixity, this B cannot go up and down. So B is a hinge, is in position, cannot be lifted. Now, if you have to go up means you have to bend it. Bending deformation is not possible. So, it remains here only, C remains there only, that means it behaves like a simply supported span. So, simply supported beam concept you have to remember. See here, this is a simply supported beam, let us say. You cut here, what you have done? Left side piece down, right side piece up. This is what you have learned, total must be 1. This is what you have studied, okay. Now, theta A and theta B is same. Here rotation is theta A is equal to 1 by L. Theta B is also 1 by L. So, the total ordinate is 1. This is what I have told you. So, that should come here. So, without removing the supports at ACE, cut the beam here. Now, rotate the beam. Now, your simply supported span is BC only. Now, there AB. So, A you rotate clockwise, B also you rotate clockwise in the fundamentals. So, at B you have to rotate clockwise, C also you have to rotate clockwise. Now, after cutting it, this I have to rotate clockwise. Now, B cannot move up and down. So, when I rotate clockwise, it will go like this. Theta B is equal to 1 by L means 1 by 2. Now, you see, where I am holding the pen is C. This is LHS of C, say. However small it is, maybe small, 1 mm length is there, say. Cut here, after cutting it, this small portion is the right portion of the cut. Cut here, this is the right portion, this is the left portion. This right portion also rotate clockwise. So, after cutting here, that small piece is the right portion, you rotate clockwise. See here, I am holding here, this is the cut portion. This I am rotating clockwise like this. If this other portion is not there, it simply goes up like this. But because overhang is there, that also you have to show. This is minus, right? Now, the other portion I will show with the help of this one. Now, you see here, this small piece only, but it will go up like this. Okay, this is theta C. Theta C is equal to 1 by 2. Here also theta B is 1 by L. 1 by L is there. This rotation is this rotation. I could have stopped here. Actually, this is a dotted line. This length, for clarity's sake, I have drawn up to here, but actually it stops here only. So, like this I have shown. So, if I rotate clockwise, this is going down. Let it go down. Once this goes down, it will go up minus. So, your influence line diagram goes like this. So, whatever cantilever beams or whatever simply supported beams you have done, you do here. Without removing the supports at ACE, cut the beam at C. Then rotate the beam such that theta B is equal to theta C is equal to 1 by L is equal to 1 by 2. Then the deflected shape of the beam itself is the ILD. Okay. So, in this case, this happens to be B, this is A. This is A, this is B from here to here. In this problem, B is almost 0. If B is 0, say, then theta A is 1 by 2, straight goes up to here. Only small length will go up. So, small length went up. If it goes up because of the continuity, this will go like this. How much it is again? 1 by 2 into 2, this ordinate is again 1. So, for all positions of the moving load, shear force at LHS of C is always negative. What then 0 here means when the load is moving from A to B, wherever it is, shear force at LHS of C is 0. Only when load crosses B, shear force at C will come into picture. Once load crosses B, then shear force at C gradually increases. When the load is at LHS of C, then shear force at LHS of C is maximum. Load crosses, if the load is exactly at C, shear force at LHS of C is 0. Load moves further, then gradually it increases in this fashion. Okay, this is the process. Without removing the supports at ACE, This is what we have done. Cut the beam at LHS of C and lift the beam such that theta B is equal to theta C is equal to 1 by L is equal to 1 by 2. Then the deflected shape of the beam itself, beam is ILD for shear force at LHS of C. So, what you have to see is where you are cutting. That span, how it behaves. Will it behave like a cantilever or simply supported? Accordingly, you have to see. After cutting it, this can only rotate, this cannot be lifted. The supported span you are cutting here, observe this end. This end, can it move up and down? If it moves up and down, CV behaves like a cantilever. If it cannot move, it behaves like a simply supported. This way displacement will be. Okay. Now let us see shear force at RHS of C. How it behaves, let us see. This we remove. This is the observation. Due to fixed support at A, B cannot move up or down. So, BC span behaves like a simply supported span. That's why you have taken simply supported concept. Now let us see shear force at RHS of C. That I will show here itself. This I think I can remove. This is the reason why we are writing like that. Now let us see shear force at RHS of C. ILD for shear force at RHS of C. Same process here also, without removing the supports at A, C, E. Now where we should cut? At RHS of C. Now, after cutting this one, if I try to lift it, can D move up and down? See, at E there is a roller support. So when D wants to go up, it cannot offer any resistance. It will simply rotate, it will move up. That means after cutting, CD span now behaves like a cantilever. Because this behaves now like a free end, it's simply freely going up. But if it cannot go up, it behaves like a simply supported. So, without removing the supports at ACE, cut the beam at RHS of C. Supposing that if you want to rotate, say like this, clockwise. If I want to rotate clockwise, it will go up. When B goes up, which is not possible, if it goes up, I have to draw a curved line, which is impossible. So, you have no choice. Then after cutting it, see right side. So, rotation not possible. After cutting it, without removing the movement, hold it, lift it. So, it behaves like a rectangle. Then D goes up, this will come down. Like this. It goes up to here straight line, then it will come down like this. This is plus, this is 1, this is also 1. This is the ILD for shear force at RHS of C. Now, supposing that this idea we didn't get, we want to rotate as in the earlier problem. If you rotate it like this is theta C. Extend this line. Assume that you are trying to rotate like this. You rotate it, that small piece you rotate it. Then this only like this. Then what will happen? I have to draw like this curved line. In a statically determinate structure, this type of curved deformations are not possible. Okay, that's why this is wrong. Next possibility is cantilever. That way also we can make it. So, shear force at RHS of C means this is the procedure. Without removing the supports at ACE, cut the beam at RHS of C. Now, without removing the moment, apply unit displacement to the beam at RHS of C. Then the deflected shape of the beam is ILD for shear force at RHS of C. Now you see what happened here is not. This is the reason, due to roller support at E, T can move up or down. So, after cutting at RHS of C, CD behaves like a cantilever beam. That's why cantilever concept came into picture. Now, why the curved portions are not possible is that also you can write. Assertion and reasoning type you will get. In a statically determinate beam, influence line diagram for reaction, shear force and bending moment are always straight lines. Assertion. Why? Because after removing the support or cutting or assuming an imaginary hinge, will make the structure unstable. In an unstable structure, any displacement you give it as rigid body, they will rotate or translate. So, the structure undergoes rigid body rotation or rigid body translation or rigid body translation only. So they have to be straight lines. Assertion and reasoning type questions, if they ask, you should be able to answer. Whether the reason is correct or not, you should be able to guess. Why they are straight lines? Why cannot be curved? In a determinate structure, they have to be straight lines. Why? You must be able to give the reason. Reason is this one. Okay, say 2 marks. Till now they didn't ask you this assertion and reasoning type. Now in the gate also multiple assertion and reasoning type they don't ask you, but in the prelims they will ask you this type of assertion and reasoning type questions. Okay. Now, let us see ILD for bending moment at C. Okay. Influence line diagram for bending moment at C is 4 diagrams they give you, you must select the correct one. For that, first we should know how to build it. Now this is ILD for bending moment at C. What is the process? At the support, either it is a fixed support or any intermediate support, process is same. At any intermediate support or fixed support, the support cannot be lifted, because when you assume an imaginary hinge and it is not possible to lift it because of the reaction. So, without removing the supports at A, C, E, assume an imaginary hinge at C and apply unit rotation. The deflected shape of the beam itself is the ILD for bending moment at C. This is the process. Without removing the supports at ACE, assume an imaginary hinge at C and apply unit rotation. Deflected shape of the beam itself is the ILD for bending moment at C. Now you see A, this point let us say A, C, E. Assume an imaginary hinge and apply unit rotation, say clockwise, because it should go down like this. Theta c is equal to 1. Then naturally it will go up. Then what is this length? 2 meters minus, that's all. You may get a doubt that what happens to the left portion. We will try left portion also if you give that rotation, say like this. Supposing that, then B cannot go up. If it is going up, what I have to do? I have to draw a curved line like this. Determinate structure, curved lines not possible. So entire diagram not possible. So only this you cut it off, because you don't know. You may have to sometimes make a mistake there. As per this your thought you draw, if you get a curved line, so that entire process is wrong. Next process, that means this side there will not be any influence of unit load on bending moment at C. When the load crosses C, only then influence of unit load on bending moment at C will exist. So you see here, when the load is moving from A to B to C, bending moment at C is 0. Why? For all positions of load here, I will cut here, look right side. What is reaction at E? Reaction at E will exist only when the load is here, but load is not there. So V is 0 when the load is here. So once V is 0, 0 into 4 is 0. So for all positions of load here, bending moment is 0. So influence is 0. When the unit load is here, bending moment at C is maximum. When the load crosses D to E, if it goes, the influence gradually reduces to 0. That's how it should be drawn. So all quantities we have finished for cantilevering portions, simply supported portions. Once you cut a section in any continuous beam, wherever you are cutting it, how that span behaves you have to see. Will it behave like a simply supported, or after cutting one end freely it moves up and down? Accordingly, cantilever concept or simply supported concept should be brought in. Okay. Now let us see, again let us go back to our simply supported beams.